Hello friends, today we are going to discuss about different type of forces. So I'm taking few example. Please tell me the force involved in the each case. If I drop this duster, it will move in downward direction. It is a very common question. Why it is moving in the downward direction? Why it is not moving in upward direction? Why it is not moving in left direction, right direction? What is the answer of this question? Why it is moving in downward direction? The answer is everybody knows the answer, because gravitational force is acting in the downward direction. Now what is gravitational force? The answer is every mass attract other masses, and this force is known as gravitational force. So gravitational force is force acting between masses. Here now second is electrostatic force. Student, tell me, if I take two charged balloon, they will repel each other. If I take a charged scale or charged pen which is rough with my hair, and if I keep this pen near to the paper pieces, you have done this activity, it will attract the paper pieces. Why? Because it has been charged and it is attracting the other charges body. The force of attraction or repulsion between the charged body is known as electrostatic force. So I am drawing here. Suppose I have taken this charge. This one is positive charge, this one is positive charge, so both will repel each other, and that force of repulsion is known as electrostatic force. This one is electrostatic force. Is it fine? So electrostatic force acts between the charges. Now suppose you are having a rubber band, elastic rubber band or a spring. As you stretch it, it will oppose. It don't want to stretch, it apply elastic force in opposite direction. So friends, now we can divide these forces into two categories. The two categories are conservative force and non-conservative force. Now let us see what is conservative force. It is force by which work done does not depend on path. Please notice this point. Conservative forces are forces by which work done does not depend on path. It only depends on initial and final position of the body. The example of conservative force is gravitational force and electrostatic force. Spring force is also example of conservative forces. Now let us see what is non-conservative force. Work done by these forces depends on path. The example of non-conservative forces: frictional force, air drag, viscous force. These are the example of non-conservative force. Friends, now we wanted to know about gravitational force, that it is conservative or non-conservative. So for that we are doing a very simple activity. Suppose I leave this duster from h height and I wanted to know the work done by gravitational force. In this way it is moving. So work done by the gravitational force will be, the formula of work done is force into displacement. The force is here mg. You know what will be the gravitational force on the duster? It will be mg. So force involved is here mg and displacement is depth h. So in this case the work done is force into displacement. Force is mg and displacement is h. So the work done will be mgh in this case when the duster is moving on the straight path in the gravitational field. Now suppose I change the path and I wanted that the duster should move on the inclined path, but it will travel the same depth. Let us see. You will answer me either I have changed the depth or not. It is moving on the same path. It is moving on the same depth, but the path has been changed. It is moving on the different path, but depth it is traveling, that is same. So in this case, is the work done will be same or different? What do you say? It should be different. It might be same. Let us calculate. So first of all, I draw the situation. This is the inclined plane. The duster is moving like this, but it is traveling the same depth h. Path has been changed, but the depth it is covering is still, that is h. So when the duster was in between, if I mention the forces, the gravitational force is acting in the downward direction. If I make the component of this mg, it will have two components, this one and this one, because I have taken this angle theta. So this will be theta and this component will be mg sin theta and this will be mg cos theta. So now along the inclined plane, the force acting is mg sin theta. Initially in the first case, the force was, what was the force? Mg. But now the force has been reduced to mg sin theta. So you noted the point. You have taken the longer path, but you have reduced the force. That's why the work done may be same. I'm not saying that it is exactly same. It may be or may not be same. Let us see. So we have to calculate the work done in this case by the gravitational force. We found that the still force is mg sin theta and displacement is, what will be displacement? Yeah, it should be the displacement, and to find it, what I do, I use the simple trigonometry. I do h upon, suppose this inclined plane length is d, so I do h upon d. H upon d is sin theta perpendicular upon hypotenuse, so d will be h upon sin theta. Now I am knowing force, I am knowing displacement. In this case force is this, displacement is this, both will be cancelled and the work done is mgh. Yeah, in this case even the work done is mgh, that is equal to first case. So what it proves, on changing the path, work done is still same or different? It is same in the both the cases. We are doing, the gravitational force is doing same work in both the cases. Now we can say that gravitational force is conservative force. Work done by the gravitational force does not depend on path. If you have chosen the longer path, you have also reduced the force. That's why work done is still same. Is it fine? And in this case you have reduced force but you have chosen the longer path. That's why the answer is coming same. The work done by gravitational force is still will be same. So what is the conclusion? Gravitational force is conservative or non-conservative? Conservative force. Similarly, electrostatic force will be conservative. Spring force will be conservative. These forces are in category of conservative forces. We have conclusion that gravitational force is conservative in nature and the work done does not depend on path. Even you are taking this path, work done will be mgh. In this case, the work done will be mgh. And suppose I have taken another path, it is having very lesser slope. In this case also the work done will be mgh. So now what is the difference in all these three cases? The difference is, if you have to put the object from here to here, in this case you have to overcome the force mg. But in this case, if you have to put the object from here to here, you have to overcome the force mg sin theta. In this case you have to also overcome the force mg sin theta. Here the force is least but the path length is greatest. Here the force is increased but path is reduced. Here the force is greatest but the path length is shortest. But in all three cases, work done is same. And I'm very happy to inform you that this fact was used. I suppose that this fact might be used in forming one of the seven wonder. Can you guess? It is made of huge rock structure. Can you guess the structure? This is pyramids. Actually, you will listen to shock that pyramids are made of so heavy blocks that blocks can't be lifted up to that height with the help of today's era machines. We don't have such machines which can put those heavy stones to up to that height directly, even in this time. So now question is how they have done so earlier. The answer is they have reduced the force by changing the slope. They have taken this path which is having very less slope. Actually they have taken the long path but slope was very less. That's why they have to overcome very small gravitational force. They have chosen the longer path, so the work done was the same. Gravitational force is conservative in nature. If even you take the stone in any way, in all the cases the work done will be same. But because we have taken very less slope, that's why mg sin theta, the gravitational force which we have to overcome, is very less. And this is the key fact behind how they have placed so heavy blocks up to that height. Friends, now we are going to discuss what happens when an external force do work against conservative force. So let us see. We are taking a very simple example. Suppose I have to put this ink bottle from ground, suppose here it is ground, to this height. So what I need to do? I need to apply some force in upward direction. Let us see. As you are trying to move this bottle in the upward direction, because gravity is already acting in which direction? Gravitational force is acting in which direction? downward direction. So already gravitational force is acting in the downward direction. So to move this bottle in the upward direction, you need to apply an external force, and this external force should be greater than the gravitational force. If this will be greater than, then the body might be accelerate because the net force is acting in the upward direction. So I suppose that I don't want to accelerate this bottle, so at least I want external force is equal to gravitational force. Let us see. And I'm smoothly moving this bottle with the help of external force, and I'm putting it here. So while I was putting the bottle, I need to apply an external force against of conservative force, and that should be equal to at least conservative force, or we can say gravitational force. It should be at least equal to that. Even I don't want to accelerate the bottle. In that case, I need the external force equal to conservative force. So I just put this bottle and I move this in upward direction. The external force is here in the upward direction, that is equal to conservative force, and I'm not accelerating the bottle. I'm just smoothly moving it, and I'm putting it here, like here. I'm just moving it. I'm not accelerating it, and I'm smoothly moving it, and I'm putting it here. Now see what happens. External force is doing work against the conservative force. So what happens here? See, is this bottle is having some energy now? Let us check either it is having energy or not. Let's push it. It is able to move now, so it should have some energy. Fine. And this energy is known as potential energy. So always remember, whenever an external force do work against any conservative force, then body acquire an energy, and this energy is known as potential energy. See here, work done by the external force. Work done by the external force against conservative force is stored in form of potential energy. Is it fine with you? And what amount of work is done by the external force, that convert in form of potential energy to the body, that is stored in form of potential energy to the body, and that is also equal to negative of work done by the conservative forces. Both the forces are equal in magnitude and opposite in direction, so that's why its work done will be negative, and work done by the external force will be equal to work done by the conservative force, and that is equal to energy stored, potential energy stored in the body. So remember this point, that potential energy is equal to work done by external force or negative of work done by the conservative force. Now see here student, what I have assumed here, I have assumed the bottle on the ground, and on the ground we suppose potential energy 0. So always we have a reference in where we consider potential energy 0. Here potential energy is 0 on the ground, and we move this body from 0 potential energy to this height. At this height, potential energy is equal to work done by the external force or negative of work done by the conservative force. So always remember, the potential energy is equal to work done by external force in bringing body from 0 potential energy, where you have supposed 0 potential energy, to any position. Once I'm again repeating, the potential energy of a body is equal to work done by external force in bringing it from 0 potential energy, where you have supposed, to a particular position. Here the potential energy of the body will be equal to work done in bringing it from 0 potential energy, that is ground, to this position. So I'm just repeating it again. Please remember this point. There are the two important concepts. The first point is potential energy is equal to work done by external force or negative of work done by the conservative force. This is the first point. The second point is that this work done is from 0 potential energy to any position where you are defining potential energy. Suppose I am defining potential energy here, then moving the body from ground to this position, and potential energy at this position will be equal to work done by external force in bringing it to ground, that is zero potential energy we have assumed, to this position. Is it fine? So please remember, once again I am repeating, potential energy of a body or system is equal to work done by external force in bringing it from zero potential energy position to any position. Let us see in case of a spring what happens. Suppose you are having a spring and the spring is having natural length. In case of it is having the natural length, we consider its potential energy as a zero because it is stable now. Suppose it was initially in unstretched condition, it was in equilibrium, its potential energy was zero. As I try to compress it in this way, I need to apply an external force in this direction to compress it. In this case, the spring will apply force in which direction? The spring will apply force in the opposite direction. Now see, is external force, this external force is doing work against the conservative force. Here the conservative force is, which one is the conservative force? Spring force, elastic force is the conservative force. This one is the conservative force. And applied force is doing work. Applied force is doing work against the conservative force. See here, this one is applied force, this one is applied force, and it is doing the work against the conservative force. That's why this spring should store some energy, and this energy is known as potential energy of this spring. Now see, as I leave this spring, it will just again gain its original shape. It do some work, means it was having some energy, stored energy inside it. So this energy is known as potential energy of the spring. So always remember, potential energy of a spring you will define as when it was in a unstretched position, when it was on its natural length, its potential energy was zero. We do some external work and we compress it. And potential energy is work done by external force in compressing it from its original length to this compressed. In case of electrostatic forces, what will be meaning of potential energy? Let us see. Suppose two charges were at infinity. Infinity means they were very far and they were not interacting, they were not applying any force to each other. I bring one of the charges near to this charge in this position. When I was bringing this charge, both are having a positive charge, so repulsion was acting on it. This is the electrostatic force as well as conservative force. To bring this charge, I need to do work against this conservative force. So I applied this force, externally applied force, opposite to that conservative force. Means here again, I need to do work. Suppose this one is Q1 and this one is Q2 and Q2 was at infinity. As I bring it near, I need to apply force against of conservative force. So again, same situation is taking place here. The applied force is doing work against the conservative force. You can see, means the body will acquire, both the charges will acquire potential energy. And here the potential energy again of this charge system will be work done by external force or negative of work done by the conservative forces. But the condition is, we are bringing these charges from initially zero potential energy configuration to this configuration. Initially the charges were at infinity and we kept them on the finite separation. When they were at the infinity, their potential energy was zero because there was no force acting between them. From zero potential energy state to the particular configuration, from zero potential energy configuration to a particular configuration, we bring both the charges with the help of external work, and this work done by external force is equal to potential energy of this system. So again, we can define here, potential energy of both the charge systems is equal to work done by external force against conservative force. So friends, we have seen that work done by conservative forces does not depend on path. It only depends on initial and final position of the object. Now I am again rubbing it. In the second case, I feel that temperature is more than in case of first case. So what is the reason? The reason is here work done by friction. Here the work done by friction is on longer path. That's why more heat is produced, more work is done in the second case. Am I right? More work by the frictional force has been done in the second case because frictional force was acting for the longer path, right? So the more work has been done in the second case means work done by frictional force is depending on the path length. Fine. So we can have the conclusion that work done by non-conservative forces depends on path. I am having in one more example. You can see here, this is known as frictional welding. In case of first case, when they are rubbed less, less heat was produced. But in second case, when it was rubbed continuously and friction was acting for the longer path, then more heat was produced. Means in second case, more work has been done by frictional force. Work done by frictional forces depending on the path, and that's why we can say that work done by frictional force depends on path. Work done by non-conservative force depend on path. Friends, difference between conservative and non-conservative forces. First point, work done does not depend upon the path in case of conservative force. But in case of non-conservative force, we know that work done depends on path. Now second point, work done in a round trip is zero in conservative forces. But in case of non-conservative forces, work done in the round trip is not zero. Mostly the conservative forces, all the conservative forces are central in nature, but non-conservative forces are velocity dependent and retarding in nature. In conservative forces, the mechanical energy of system is conserved, means total energy, that is kinetic energy and potential energy, sum of kinetic energy and potential energy is always constant. If kinetic is increasing, potential will decrease. If potential is increasing, kinetic will decrease, but total energy remain constant, as we have seen in case of freely falling objects it occur. But in case of non-conservative forces, work done against non-conservative force may be dissipated as form of heat, vibration and sound energy. Work done can be recovered in case of conservative force, but in case of non-conservative force, work done can't be recovered. For example, we are taking one example. If I pick a ball on some height, or I stretch a spring with some length, as I will leave, the spring will move, the block will move with the spring, the ball will come down, means it is reversing back as work. But in case of frictional force, it is not taking place. Thank you, Pichu.